All right, thank you. All right, can you hear me? It's good. Okay. All right, so today I'm going to talk about towards solving inverse graphics problems in the wild, particularly for end-to-end approaches. By the way, please feel free to interrupt and ask questions on the way. Okay, so let's start by looking at this image. What can you say about this picture? First of all, we know that it's a cat, but we also know that it's a cat that is in a sitting position. The pose is like so. We know that because this is a cat, there's ears underneath this box. We know that this box is a Chinese takeout box, and the color of this box is all white. And you see some shading on the side, and that's because there's a lighting coming from this direction. This cat is on a floor, and there's a carpet, and I can keep on going and describing about what's happening in the image. So this process is understanding what is happening in the image through different factors. And this has been a fundamental topic in computer vision. It's really all about factorization. The first computer vision paper by Roberts was also on this topic, where he took an image and tried to describe it in terms of the blocks of world assumption. There's a lot of other methods like intrinsic images, shape from shading, Tomashi Kanade's factorization work as well. And then there's a lot of work, but it's just a sample of works that models faces in a linear model of geometry and faces. And it's all about this disentanglement of what's actually happening in the image. And so these problems, we collectively call them as vision as inverse graphics. And I think this is a really interesting problem. And the work that I did during my PhD is a subset of this problem, particularly for the 3D reconstruction problem for non-rigid objects like animals and humans, where I take a single image and try to reconstruct these objects. And not all of this result is fully automatic. And today I'm going to talk about the recent stuff that I've been working in this domain for humans and for face decomposition. But what makes this problem interesting and difficult is that by definition, the problem is underconstrained, because there's many solutions that explains the same 2D observations. Another figure that I really like is that of Baron Malik, where you have this image from Adelson's paper. The likely explanation of this image is this, but there's a lot of other explanations depending on the eye of the beholder. So this picture tells us really that what is really important is priors, priors, priors. And a lot of the traditional computer vision work, and the interesting thing is that we design what are the good priors, how do we learn these priors, and then we design some kind of a likelihood function and solve an optimization problem. Okay, and so this is a nice framework, but of course we know that a lot of the progress today that is actually really working in the real images are these deep learning based approaches. So the question is, how do we solve inverse graphics problem in a deep learning setting? So in this setting, the problem is that there's no ground truth for these problems. It's difficult to obtain. For intrinsic images, it's difficult to annotate all of the albedo, or the 3D pose of a human in real images is difficult to obtain, and especially at a large scale. So a lot of the progress in this domain has been to collect lots of synthetic data. So you have these synthetic data sets, where you know you make a synthetic data set of like ShapeNet, or you can synthesize a human with a texture in a random background and then have ground truth. So now you can train a network on this. Or for human pose, you can collect human pose in a controlled environment where you actually do know the 3D joints and use this to train. So this is all nice, and even with this data, it's quite hard to solve this problem. So there's a lot of interesting directions. But the problem with synthetic data, or relying too heavily on it, is that this inverse graphics problem is reduced to a black box supervised function approximation problem, which is, I don't really find it very exciting or interesting, but also there's a lot of issues that you're really dependent on this paired input and the target. And if you don't have that kind of paired input and target set, how do you learn this function? So this is an example. Maybe you get a chair and you want to output the voxel of the chair, or you get a human and you want to output the 3D joints. Another issue with working with synthetic data alone is that there's this issue of domain gap, because real pictures of humans don't look like this. We're not in front of a green screen. Our appearance is a lot more diverse. There's a lot of clutter and occlusion in images. So models that are trained on these data sets don't generalize very well to the real complexity of the real world. So can we do something in between? You don't want to do it in an end-to-end way. But if we know the structure, we should use it. As Jitendra says, there's some God's own truth that you can inject into the network, and that will help it learn fast, learn better, and generalize more. And there are multiple ways to include the structure inside a network. Maybe it's an architecture design. Well, today I'm going to talk about a specific problem where in the form of given an input image, I want to decompose it into several latent representations. And using the latent representation, you want to reconstruct the image. So essentially, you're saying, give me the factors that explain the image. So autoencoders fall in this domain. But I'm specifically talking about a setup where the known structure, the latent space, is not just something that you learn as like a dimension, but something where you actually know what they are doing. You know how to use them because you know the physical rendering equations. So these y might correspond to geometry and shading and so forth. So of course, there's been a lot of work in this domain. It's this disentanglement or generative model learning through deep learning. But I think a lot of the work is still in toy data sets or synthetic data sets. And so today, the topic of my talk, today the things that I want to talk about is how can we make this kind of approach work better on real images? And I'm going to take two examples, 3D human mesh reconstruction in the wild, where given an image, you want to reconstruct the mesh like so. I'm also going to talk about the decomposition problem of decomposing face into geometry, albedo, and shading. This is an engineering image problem. And in both scenarios, the key is that you make use of a known structure in the world so that maybe the rendering function that comes from these latent factors are known. And you can, because you're actually explaining the image, you can train with real images. Okay, so the first part of this talk is a collaboration with my Michael and my former advisor David and my current advisor Jitendra. So again, you want to take this image and then recover a mesh from this. Okay, when I say recover a mesh, what do I mean? The mesh is represented by this Michael's generative model of human bodies called Simple. So the story is that in order to create a human body has a shape. It might be tall or skinny or short. You model these things in a linear space, the PCA. So this is beta is just 10 dimensions, and you can change the shape of the people. And then you also you model the articulation with the kinematic tree of relative rotation angles of the joints. Combining these two, you can model most humans that are adult because we don't have babies in our data set. So the shapes can't handle babies, but for adult babies. So, and then we also want to solve the camera. So this is the representation. So when I say recover mesh, I want the network to give me beta and theta. Theta is 23 3x3 rotation matrix in the camera. So it's relatively low dimensional. In total, there's like 85 dimensions that we need to regress. But the nice thing about having a mesh is that you can do a lot of things like foreground, part segmentation. And because these mesh is parameterized, so once you fit the mesh model to an image, you have a dense correspondence between one person and a different person. This is also very useful. And this is another advantage over voxel kind of methods, because if you do voxels, you actually don't get correspondence. You have a shape, but you don't know what that means. Here, if you do this, you actually know exactly what the vertex is for each image. If you have mesh, you can also recover this. It has a lot of graphics uses. And another nice thing is that because I'm always outputting a whole mesh, it's by definition amodal or holistic, so we can infer about the parts that we don't see. So there's a lot of work in this domain, and there's a lot of work from Kostas's lab here, and in regressing the 3D joints of images humans. And here I just want to make clear that if you want to attach a skin to the kinematic model, you actually have to solve for the twist of the joints. So joint locations alone are not enough. Yes?
Sorry, is it accepted or is it controversial that 10 eigenvectors would suffice to define, to give a good body shape? How controversial is that?
I'm not so sure I'm not sure if it's controversial. It's definitely low frequency. It doesn't capture like high frequency information about the body. But another thing is that unlike faces, human bodies you could probably get by with a low dimension. We're still not at the stage to get really high frequency like wrinkles of the bodies or.
I guess my question is your accuracy results for I hat minus I are going to be confounded by the goodness of the eigenvector system, right?
Right.
Do you know how to control for that?
Yes, so when they made the model, they had this kind of experiments, like trying to measure how much does it capture the variance. And it does pretty well. And I think 30 components capture like 99%. I think 10 is like 98, but we just use it for this purpose. It's also like, it's not that we don't really have a very good signal for the shape also. It's very difficult to get this kind of shape ground truth. So that's, yeah.
But it could be the fact that it could be very well a three-dimensional but highly nonlinear manifold rather than, a 10-dimensional linear thing.
Yeah, and so we're making a linear assumption. Yeah, and that's not it might not be true. It's for you. Yeah, it's a model. Yeah, it's a. Okay, so what was I saying? I was saying that I actually have to solve for the rotation as well. So not just joint locations. And in my previous work, I did this. That work. This is also my work where we used an optimization method. So it's the same sets of parameters. But there, I was minimizing these parameters to explain the 2D points. So it wasn't an end-to-end, it wasn't learned method. And more recently, there are methods that tries to output the mesh of a human face from images. But humans are a lot more challenging because they're articulated. And their face approach is also fully supervised. They could just capture a lot of people's faces in a lab and have ground truth scans. So in this work, we output a lot more. We also output the shape and the limb orientation. And I'm going to discuss about this further, but our network can be trained in a weakly supervised fashion with just set level supervision. I'm going to get into this further. So we're solving this in a real-time approach because the optimization-based approach takes like a minute, and it's throwing away a lot of information, and then we're dealing with articulation in an end-to-end manner. Okay, so again, the problem in this is that you don't have the paired 2D to 3D labels. So for green screen images, you can get these 3D joints. But for real images, what are the 3D joints? It's difficult to annotate, especially at large scale. And of course, there's this problem of depth ambiguity. Okay, so our idea is that we notice that even though we don't have paired 2D to 3D labels of real images, we have a lot of unpaired labels. By unpaired, I mean I have a lot of images with 2D labels because as a community, we collected a lot of these. So we have images with known 2D joint locations, but we also have 3D scans. When we were building this model, they had a lot of scans that might not necessarily come with an image or the image is in a controlled environment. But we have 3D scans in the same representation, the same mesh representation that I was just talking about. So these are independent, meaning that I actually don't have the 3D of this particular human, but I have a lot of examples of different humans. And so what we're going to ask the network to do is to explain the 2D pose while staying within this distribution. So this is the key idea. And the nice thing about this is that with this framework, you can train a model that infers the 3D without actually having paired examples of this is the image and this is the 3D. So the architecture that we do for this is that given an image, we have a network which is going to output regress these parameters, including the camera and the rotation and the shape. By the way, which is a very challenging problem because you actually have to reason about the global orientation as well as how the human is articulated. It's quite ambiguous. Maybe if the scale is off, everything is wrong. Okay, but given these parameters, you can create a mesh. From the mesh, you can get the 3D joints. You project them using the camera that you estimated, and you get a projection of estimated 2D pose. And now you can use this reprojection loss to train this. But again, this alone doesn't constrain that the 3D humans are reasonable. So we're going to send this to an adversary. And for this, I use a discriminator. And to learn what humans look like in this space. So this is an overall framework. And sometimes we actually do have 3D joints in the case of mocap. So in this, if you had that 3D regression loss, and if you ignore the rest of the part, this is a standard supervised regression problem. And in this work, we actually show that even without using any 3D regression loss, we can actually train a model with a set level supervision alone. So by this, I mean that this is a set level supervision, and I'm not using, I could throw it away. Even if I do have the ground truth 3D, suppose I don't use it, I can still train a reasonable network, a reasonable 3D inference thing, which shows that using this concept as regularizing the humans to be on this manifold is a good weak supervision. Okay, so another properties of this model is that a lot of the work infer 3D from 2D pose detections. So my previous work was that given 2D pose, infer the 3D through optimization, in which case you're throwing away all of the other image information. But here, we're doing inference directly from image, so there's a lot more juice. Because we are using this very strong human body model, the output is guaranteed to have a human structure, meaning that it could not look like a human because the configuration might be crazy. Like my neck could be like rotated like in the 360 degrees. But it's always going to have a symmetric hand. It's never going to have a situation where one arm is longer than the other, which does happen if you just regress the joint locations. And again, we have this prior that we learned on the fly. So now the question is, what do we send to the discriminator? Like, what am I going to, how do I make sure that this is on the human manifold? And there's multiple things that you can do. And as you notice, this is in this adversarial framework, which is, you know, might think that this is whatever fashion thing right now. And usually in GANs, you show the image to a discriminator, which I could have done this. I could have rendered a human and sent it to a discriminator and be like, is this a real human or not? But in this work, we actually, we noticed that the human body model has a factorization. Yes?
So on your previous slide, are you demanding that the output be one of the meshes that you like generated or something similar to that?
I'm going to get to them. So basically, these parameters that I generate should look like this in English. Okay, so what does that mean? And so what does that mean is that we notice that the body model is factorized. So this is where the structure that we know. I think it's reasonable to model deformable objects through their intrinsic shape and how they're deformed. And so that's what we do. So again, we have this shape. So we're actually going to have multiple discriminators, one on the shape, one on the whole set of rotation to model the joint distribution of the angles. But the kinematic, the articulation is modeled by a kinematic tree, which also has this conditional independence assumption. So actually also going to throw a discriminator on each of the joint angles, which basically means that this discriminator takes in a 3x3 matrix and has to say, is it okay or not? And it's a very, by decomposing these into these components, it's a lot more data efficient and generalizable because you don't have to see all possible configuration of the shape and the body. And this helps make the learning a lot easier. Because the input to each discriminator is very low dimensional, the training is very stable. I don't really experience too many difficulties concerned with training GANs. We don't get into mode collapse, which is a lot of the issues that GAN people have because we have the reprojection loss and the network has to still explain the 2D observations. And so this was quite simple for us to do it. And this is the tool that we used. And it could be a GFM, but we just used, it was a very simple way to actually do this. But this applying discriminator on the latent space, I think, is an interesting direction that not that many people have tried, but I think it makes a lot of sense. Okay, so that's that. And okay, so here we do this experience. Yes?
So how simple of a discriminator can you use in this space? Can you just use linear classifiers and it still will work?
We never tried linear, but it might as well as be linear. It's just 2-layer. Well, okay, so technically, these are all rotation matrices. And we want to learn how to embed the rotation matrices. And they all share the same. So what we do is we take the rotation matrix.
These are the coefficients of the 3 by 3 mode.
Yeah, 3 by 3, nine-dimensional values. We sent it through some layers of networks, which gives a common representation to, say, like 32 neurons that describes what 3 by 3 matrices are. And then we throw a linear classifier on top of these.
So you could probably just do it with a simple SVM.
We could, except that's why I'm saying it's like a very.
It's not sexy, but you could.
You could, but the nice thing about this is that it's easy to train on the fly with it, right? And with the SVMs, you have to first generate the bad examples, and then the good examples, train the SVM, and then update again. And this process is more seamless. So I think it's not only is it fancy, it's just like easier to do, or like simpler to train. So here's an experiment like showing like, do we really need this discriminator? Like or it doesn't have to be a discriminator. If we don't have this prior, what happens? So we did a training where we don't have any supervised pairs, 2D supervision, 2D to 3D supervision, and we don't have any prior. Then we get this solution where the configuration is just not right, okay? And it just looks weird. But notice that it actually minimizes the 2D pose very, very accurately. This is test image, and it's very good at fitting it, but the 3D that you get is not very good. And another point is that this regressing the 3D rotation is a very challenging problem, especially because you also have to regress to the global rotation. I've tried many times in the past. My collaborators also have tried many times in the past. And none of us could actually really make it work. And this is one of the challenging things. And one key to actually making this work was to do this iterative approach where the network outputs a correction. So what happens is that, so we use ResNet or something and get an image feature. This big theta is the concatenation of the current human body parameters. Given these two input, network outputs a correction, like how to fix the current estimate. You add that to the current thing, and then you get the new thing, and then you just iterate for a fixed number of times. And this really helped because solving this difficult problem in one go was too complex of a regression problems to learn. But splitting into these subsets made it a lot easier to train. This was tried in a 2D pose setting, where in 2D pose, you actually know what the ground truth should be. So you actually know how to, in each intermediate step, you know how much to correct. And so people would do this kind of supervision, like take intermediate steps. We don't know this, so we just put the reprojection loss in the last iteration. This is details. But we also send the output at each step to the discriminator. Yes?
So I wonder if it's the feedback that was important. You could have imagined doing this in multiple scale spaces without any feedback at all, right? You could have imagined trying to fit to a coarse version and then refine your version, refine your correct and keep forward. But is the feedback that's giving you the effect, or is it just that you're doing some progressive descent?
I think it's a progressive descent. And I think the nice thing about the progressive descent is that, feedback is also progressive.
Yes,
yeah.
Very specific, right? I mean, could you have done? I guess my naive question is, could you have done this just by a scale space kind of method, right? By deforming either the discriminators or the bits, the I-hats deforming the I-hat pairs.
So I think it is the scale version, but in this latent space is like one way to think about it. I mean, it's because you're starting off with a coarse estimate, and then you're slowly making it better.
That's my question. I'll
Yeah. Okay. So so we take the intermediate output and send it to the prior as well, so that the correction has to also lie on the human manifold, which is just another regressor that adds a tiny bit. But here's the iterative regressor in action. So from a given input image, we always start with this mean human body with some reasonable camera, and then the network outputs this correction step by step, and slowly it gets to the right solution. Yeah. And so another reason why this works really well is that when you do any regression problems in a deep learning setup, it's very important to normalize the output space so that the magnitude of the vectors that the network outputting is reasonable, small. By starting off with the mean, you're always, it's essentially a normalization of the space. So this is why it makes the problem really easy. Just doing one step is a lot better than not starting from anywhere. Okay. So here's the quantitative evaluation. And unfortunately, there's no 3D mesh of real images. So we can't evaluate the mesh. But fit to the mesh. So we use this more traditional 3D joint estimation problem. And so in human 3.6, the task is to predict where each joint is. Lower is better in this figure. These are previous works. So the bars in gray are the method that only outputs the joints. Bars in blue are a previous method that output a whole mesh. And so we get this, our approach is this bar, which isn't as best as the state-of-the-art numbers, but we're also outputting a lot more. We're doing so much more than just 3D joint locations. And we beat the other method, the previous method that outputs the mesh. But the more interesting question is, what if you do this setting where you don't use any paired 3D supervision, only set level? So this is a bar, and it actually does quite reasonable. It's even better than the previous approach that was based on optimization. And I'm going to show results now. So every result that is shown in pink is this setting where ground truth 3D joint wasn't used, but only set level. And for these images, I actually picked the set of result where the blue and the pink meshes were very different. And you can see that they're quite reasonable. I mean, there's some, I'm going to show more results comparing them. Okay, so here's a result that I'm showing through sampled at different error percentiles. So low percentile is we're doing good, high means we're doing bad. So this is a good result. And I'm showing the ground truth skeleton in gray and ours in blue. So already at 60th percentile, I mean, the result looks reasonable, but you can see that there is a large gap between the gray and the blue. And this contributes to the reason why we're not getting the state-of-the-art numbers in the 3D joint estimation problem, but you can see that the output is reasonable. I'm not so sure if 3D joint estimation, 3D joint millimeter error is a really good metric for this, if you can recover something that looks like a human. It's a lot better than recovering a point set that doesn't look like a human. Here's like an error mode where we didn't infer that the arm is extended all the way. Here's another result where it's actually 90th percentile. So the 3D joint error is quite high, but it's still quite reasonable. So here's more results on Coco, where there's a lot of occlusion and clutter. And notice that we're always outputting this holistic, where we can output the part that is occluded. And it works on these occluded images. I think this is the key. Like a lot of the work in 3D body analysis has shown results on the green screen data set and works really well there. Not that many results are on these cluttered images. And that was really the focus of our paper. So here are some error modes. A lot of the error mode is missing the joints. So this is a very complex, so it's reasonable. But this is supposed to be a leg, but it was an arm. But you can see that it's it still outputs something reasonable. And we also don't have babies. So this is a restriction of the generative model that we have. We never had baby scans. So our linear space doesn't capture baby bodies. So we can't model them. But okay, so here are some results on the video. I run it per frame. Yes?
Just out of curiosity, what makes like kids harder I would like.
Oh, no, it just-
I've never done anything like this, so you would
Right.
imagine intuitively it's just like small.
It's just data collection. It's very sensitive to collect babies, put them in a lab. And this was done in Germany, and it's very sensitive to, it's very, you have to put them in a very like skin-tight suit and all of these things, and there's a lot of issues. And
And maybe German babies don't look like American babies.
yeah, do you have a question?
Yeah, so you mentioned that the 3D joint angles might not be a good error metric. Is there anything known about perceptual measures of what people actually see in terms of differences in human pose? Is there anything known about real perceptual measures?
There's not that many good measures on this task. It's especially on 3D, nothing really. There's some symmetry, like the resulting body should be symmetric or something like this. There's illegal angle that people have kind of explored, but not too much, yeah. So I think it's a challenge in this field. Okay, so here's some results on the video. So this is the input. Okay, and then my method requires a bounding box. So we obtain bounding box using standard tools. And this is our output. This is a projection of our mesh using the camera that we estimated to get these 2D points, just as an illustration. And this is a visualization of the model from a different viewpoint. Here's another result in a more challenging parkour data set. And because there's no temporal continuity here, there is some jitter. But I think it's still quite challenging to do this in images like this.
You're not using any coherence?
No, I mean, I could have like done a very simple like smoothing over, but I'm just showing it raw output per frame. So in future, like the next step is to add a dynamic prior. Like we can also do the same idea. The way the human moves should be similar to how the real human moves.
And how about the initialization of your variance? You would think that there's a huge benefit in not reinitializing each time.
Yeah. We tried this. The previous frame should start off with the previous assumption. Yeah, that's a good direction to try.
Because you get cumulatively, it seems like you get a whole lot more.
Yeah, and I think the challenge there is that the network you have to train this in a sequential manner because it has to start off with a close result. And also there's a question of like, what if that was completely wrong? How do you fix it? And so there's these questions. Here's another. So there's this guy on YouTube that does a lot of different walks. And so here's an example. So blue is with 3D supervision, and the pink is where I don't use any 3D. And you can see that it's quite reasonable, which I'm quite surprised, and I think this is more exciting. Why is this more exciting? Is because this opens up the possibility that you can keep on improving the model through 2D images alone. You don't need to capture 3D scans, or you don't need to capture paired image to 3D joints. So as a recap, so the point is that when there's no 3D ground truth, weakly supervised by forcing the latent factors to be on the human manifold. And we present our way to do this, but this is the idea to train this in a weakly supervised manner. Only with state level supervision we get a quite reasonable result, and we just use the adversarial loss as this data-driven prior. Okay, so moving on to the next section. Any questions? Okay, good. All right. Okay, so now I'm going to talk about the work I did with people at Maryland, my advisor in Shomodip and Carlos. So here is also another inverse graphics problem. It's not 3D, but it's related. So given this image, we want to decompose it into geometry, shading, and albedo. This is the intrinsic image. It's related to the intrinsic image problem. And then if you have these components, you can do things like relighting. And this is one of our results. Okay. Again, this is a challenging problem because there's no ground truth of real images. Maybe the surface normals you have from Kinect scans, but not really that many large scale. And so people use synthetic data. So other ways that people have tried to solve this kind of related problem is that they only solve for one component, like geometry or the lighting. There are methods that solve for all components like we do as a factorized autoencoder scheme. So this is very close to our work from CVPR 17. But this is used for image editing, and it wasn't actually evaluated as a method to get the geometry because it's quite blurry. And then here's another attempt at doing this with the linear model. So I think this is a case where using a linear model, you lose a lot. Especially in faces, you see a lot of uncanny valley because it can't really model high frequency geometry information. You can see that the reconstruction and the input has quite a big difference. So our work approach is also about decomposing it into all components and solving it all at once using a reconstruction loss. So yeah, given you want to decompose it such that this distance to that is close, we get the mask using some mask phase fitting approach to ignore the background. And we propose the architecture that is inspired by shape from shading. I'm going to get into this further, but one way to solve this problem is to just deal it as an image translation problem. Given an image, just do a three-way split. Give me shading, normal, and lighting. That's not what we do because it's you want to infer the lighting based on the geometry and the albedo. And then we do this bootstrap training with synthetic and real to make it work on real images. So here's the architecture where given an input image, you extract some convolution layers, and then we make an explicit branch for normal and albedo independently. And we then estimate the light. So this is where it's slightly different from the past works, which they just had three different ways to do light, albedo, and normal. But we estimate the light through the latent space of through the latent representation of the normal and albedo, which works a lot better than just doing a simple three-way split. And the light is represented in terms of spherical harmonics. You can send this through a function to multiply it with the geometry to get the shading. And then final image reconstruction is done by multiplying the shading and the albedo. And you want the reconstruction to be close to the input image. If this is synthetic, we have the ground truth albedo and normal and shading, so we use it as a supervision. And then we do this bootstrapping trick, where we first train a simple skipnet-based architecture that's a pix-to-pix kind of image translation method to train on a synthetic image. Now we run this on real image, which gives you this, yes?
I'm sorry, why wouldn't you just find down the gradient of the I minus I hat error? Why would you train it all if you've got this I and I hat coming in? Yeah, why wouldn't you just take the reconstruction, subtract it from the input, and move around in the parameter space of your approximation? So
that's you mean like, okay, you mean like, why don't I keep this all a black box?
Yeah.
Yeah, okay, so previous workers have tried this and it's not, okay.
But you have a structured box, you know, box, right? Why don't you just move your gray box parameters with the gradient of the
Well, okay, so if the inside is just a black box, such as an autoencoder, and the problem is that the latent space might correspond to geometry or the lighting, but we don't really know, right? Here, how these components are put together is based on the actual physical rendering equation that we actually know. This helps us actually, the latent space have a specific meaning. Because
why don't you pull back the error into those different parameter spaces? Pull back the error between them.
Oh yeah, we do, but then if we don't, you mean like why do I add supervision on each of these components? Okay, if we don't do this, then there's this ambiguity problem. And there's each component can bleed into each other. So for example, the person might have a lighter skin and the color of the light is orange, but it's not clear whether it was the orange light or the white light. Yeah. So that's why the synthetic data help. And this is why we need to do this bootstrapping to make sure that these branches don't really mix into each other. So what we do is we train on a synthetic. We apply it on a real image to get these noisy outputs as pseudo supervision, and we train again with the whole SFS net with the low weight on these pseudo, but most important thing is the reconstruction, and we use just to guide the thing. And this is a lot of details about the current approach. So this is a detail, but to do this image-to-image translation tasks, the most common architecture is this unit kind of architecture, where you have this encoder, decoder output, so there's image and output image, but each layer has this skip connection to the decoder. This helps carry over a high frequency from the image, because you basically get this image and you're like, it's more like a filtering method, and it creates, it's very nice for doing image-to-image problems, and this is a more common architecture. Using residual block wasn't, it is starting to, but it's not explored as much. The thing that we noticed was that the skipnet is very good for high frequency image translation because it's very good at copying like the edges. ResNet can also, but it's more prone to overfitting. But maybe that's just an observation. But the one thing is that if you use skipnet, the inside latent space is not meaningful because most of the work is done by this skip connection. And they can basically bypass this. And if you open this network up, the latent space is very sparse. And so whenever you want to do lighting estimation from inside, it doesn't perform very well. But when you use a residual block, because there's no skipnet, it creates a much more meaningful latent space. And these are small tricks if you are doing an image translation problem that you might want to take a look at. Basically, we just use this to train this network and get the results. Yeah.
So when you do the bootstrap, it sounds like that is pretty much the key to make it nudge towards the right decomposition. Because if there's bias, it will nudge in the wrong direction.
Right.
So do you have any idea of how accurate the synthetic data have to be and how much data?
We didn't do an ablation study of like a number of synthetic with the performance, okay, so if we don't have this pseudo supervision, it doesn't work. It starts bleeding into each other. Yeah. And in the paper, there's a more ablation study that led to why we are using this architecture and so forth. Yeah. But we didn't put a lot of effort into the making the synthetic data better. We just made it once and it wasn't too much work there. Okay, so here's a quantitative comparison with the previous work. So given this input image, this is our reconstruction. And it's shown in the blue is the neural face work and the red is our work. And you can see that ours is a lot better reconstruction. Here's the geometry and the albedo and the shading. And the previous work is a lot more blurry. It's because they were using a vectorized latent space, and they're also doing this simple three-way split. Here's another result. Oh, this is comparison with the linear-based model. So MOVA you can see that our reconstruction is a lot better. And here's the albedo and the geometry and the shading. Okay, so we also compare with method that only recovers geometry. So this is our geometry, and we relight it to evaluate whether the geometry is reasonable or not. This is like looking at it from a different viewpoint. Here's the result of pix to vertex, which works really well in certain cases, but when there is a strong shadow or lighting, it's not very robust to this because it's not reasoning through. And pix to vertex is a network that is trained just from synthetic. And they fit a mesh to, this is after post-processing. And so this is the raw output of the normal, which is a lot more noisier. And then we can also do this light transfer task. So this is another way to evaluate whether your decomposition is good or not. And so what you do is, given a source image, you take a target, and you want to relight this target with the source lighting. Okay? And notice that these target images are very orangey because the light was orange. It's not that the person's skin was orange. So here's the shading of the, so what you do is you compute the decomposition for each. So the shading of the source, and you have a shading of the target, and then now you relight the geometry and albedo of the target image with the shading of the source. So this is just only showing on the transfer on the geometry, and this is the result of the light transfer. Okay, so what they noticed is that you wanted to decompose this orange image into orange light, normal human skin albedo, but previous work, you can see that the shading doesn't have very yellow on it. But our shading does capture the yellowness of the light. Because of this, when you look at the relighting, the source image doesn't have an orange light. But in this transfer, the orange light is still there, showing that the decomposition wasn't done properly. But in ours, the lighting is properly taken, factorized in the shading. Okay. Okay, so now we have some numerical results on the photo face data set, which has a very accurate normal computed from photometric stereo. Orange are the methods that's taken out of the box. So it wasn't trained on this data set. Higher is better, and we do the best. And this is a supervised method on this data set. We're already doing better out of the box, but when we fine tune on this data set, we do a lot better. And this is interesting because this method was focused on just getting the geometry. We reasoned about all, and then we're still getting, we're more robust to lighting changes. This photo face is quite a challenging data set with lots of cast shadows. And then we use the good old multiply as a test set. Here, the higher is better. And we also do better than the method that only gets the light, because we're jointly solving for all the components. And here are more results on challenging faces. So you can see that in the first row, this is a very hard example. So this is like failure case / challenging results. So there's a lot of this big cast shadow from the cap, which we can't really decompose because our spherical harmonics assumption can't handle cast shadows. But the relighting is still doing something. And these are also, this is a hard example because there's a specularity over here that we don't capture, so there's some whole artifacts in the end. So these are areas for improvement, and these are difficult faces. Here are more results that we show, and then we relight.
Do you do any evaluation of the actual 3D model that you can iterate back from the model? Because the results can be very deceptive, especially given the probability.
So the photo face does evaluate the normal. So that's a quantitative evaluation of the geometry.
The models might be actually systematically wrong, and if you look at it from the side, it's a very shallow face.
I see. Because you're not really just getting the orientation and not the magnitude. I see. Yeah. So we don't convert them into mesh. But we could, and we could visualize it from a different viewpoint. So one thing that we do is to show relighting of the geometry from different lights. And this without the relighting result, I think it's just showing a reconstruction from the same viewpoint, and that could be more deceptive. And we try to do this relighting version, as a different viewpoint. And you can see that you can see the geometry there a little bit, Okay, so the take-home message, that's it. And the take-home message is that solve more. Sometimes you solve more, and you can actually use the structure that we know about the image. And then having the structure is already a prior. And then enforcing some kind of prior learning into it with the reconstruction loss lets you train more with real images so that it doesn't have this domain gap problem. And so future work. So with the 3D human work, now we can recover these meshes, but what are they good for? So we're trying to apply it to robotics and hopefully get like a human controller from video or something like this in future. And another question is that to make this human work happen, we had to have this simple generative model of human bodies, like this mesh. But like, where does this come from if we couldn't scan people and then do this alignment and lots of hard work done by researchers? So the next thing that we're looking at is how do we learn this mesh deformable 3D model just from images and the reprojection loss. And I think really the big question going forward is how do we discover the factors of variations? So here we are like, oh, here are the latent factors, and here are how you combine them to create the image. But you want to do this discovery on its own through interacting in the world. So this is something that we can do, but we don't know how to do this automatically. I mean, autoencoder is doing this, but you don't know that it's actually doing the right thing. So how do you do this in future is, I think, a big question. And with that, and more results on the 3D humans, I'd like to end and take questions.
One encounters a growing number of religious end-enders these days. I'm wondering if they're going to tell you that you shouldn't waste your time using your human intuition about these decompositions or the factors of variation. Just find some way to apply more data. Is there a more fundamental way to address that question? To the virtue of decompositions of either mathematical or physical decompositions relative to the end-to-end making?
So I think this kind of problem, this is why I like the inverse graphics problem, because you can't just throw a network on it because you don't have the image and the ground truth pairs.
There's various ingenious ways to do self-correction, right? To do self-supervision, predictive features, and hats and things like that.
Uh-huh.
Well, they tell you just not being smart enough in your definition of what hats should be and the predictions that
I think a really good argument is that if you just reconstruct I hat, and with the black box latent space, it's not very clear how you're going to do, what you're going to do with the latent space. Maybe the latent space is useful for doing some other task, in which case I think that's a great formulation. But if you use the decomposition that we know, we can actually start doing things with the latent space. So with this face model, you can get the light and use that as a cue for doing some other task that we actually know. So I think it's clear that you can't just throw a black box on it, or to me. And I also don't think it's a very interesting approach to do it. It's not very fun. I mean, we have all these intuitions, and I think it's okay to use them when they are good.
So one of the key underlying themes of your research, which I really like, is the fact that in addition to being able to use the DNN to learn the priors, actually learn the priors and the joint. But that also has this danger of actually learning the wrong priors, right? Like what I was asking about nudging the decomposition.
Right.
So what are your thoughts about?
Yeah, I really think for this, you need the agent to actually explore in the world. Like one way to make sure that your decomposition is right is move around and look at it from a different direction and make sure that your decomposition there and the decomposition here agrees. Okay, maybe this is multi-view. If you had multi-view, you could do this. So multi-view is one answer for this, I guess. But I think you can't just, I think interacting with the world, I think is key to doing this. Yeah.
I just had a question about when you were encoding the priors on the configuration of the structure before. So you mentioned that you were doing this by simply looking at individual 3x3 matrices associated with each of the relative joint positions, and that was a surprisingly effective prior. Struck me that you could, with very little extra effort, address correlations between joints by simply looking at products of rotation matrices, and then you could have as many of those cross terms if you wanted in exactly the same framework. Am I correct? Or?
Yes, you could. I mean, you look at the okay, but just to clarify, we do send all of the rotation matrices together to model the correlation as well. So we are modeling not just the joint.
Right.
Yeah. So we do this by sending all of the rotations to another discriminator. That's
right. But all the couple of discriminators. So then you're looking at all of those rotation matrices at the same time, or
at the same time. So we do one that does everything at the same time. And individual ones also has to do the right thing. So the thing is, if you just do the overall one, the network doesn't know what to focus on and be like, overall it's kind of right, but then my knee might be bent in the wrong direction, but everything else looks right, so I'm going to say okay. And so this is why you need the individual joint constraints. Yeah. And in previous work, or in a lot of other settings, you specify these by hand, which you can do because we know our biology, but I think it's neat that we don't have to go in and specify this by hand, especially for like spines, it's not very clear what is the right degrees of freedom. And so this is one of the reasons why I like this approach. Yeah.
So do you have an overall discriminator for the whole body and the individual joint, or just the individual joint?
Both. So if there's 23 joints, there's 24 discriminators.
Okay.
Yeah.
So yeah, just to follow up on Dan Kodachek's comment. So, I mean, this works well in the vision domain where you have inverse graphics and kind of your idea of structure and kind of how they combine to give you the generative model. Have you thought about if you can, what would you do in, say, other domains like language or, you know, if you're trying to learn chemical structures or those areas, how would you actually try to factorize and get this information?
So I'm not very familiar with NLP or other domains, but if there are physical equations that explain inverse rendering equation similar to that, I mean, I think you could use this kind of decomposition. I think the key is that you want to do an autoencoder, but you want to restrict the way the latent spaces interact with each other to recreate the image. And I think this